Oh, the weather outside is, and the fire is so, with no particular place to. Let it, let it, let it. You and I make a good team, all right? That was well done. Nice job. Okay, let's get going. Now we've done electrostatics. Now we got to get into current electricity. Current electricity. I'm not talking about electricity 100 years ago. I'm talking about electricity today. Current electricity. Funny. Okay, yeah. Current is the flowage of electrons, or actually it could be protons. It could be positive particles as well. But typically when we talk about electric circuits and current, we're usually talking about the flowage of, I like the word flowage, by the way. You're gonna find that out. The flowage of electrons. Okay, so electrons moving and then doing some work. We get them to, when they move, we have them do work for us, like light a light bulb or turn on your strudel maker, or your coffee maker, or whatever, whatever it is that we use it for. Okay, current is, again, I use the word again, flowage. Now, we know what current is in a river or a stream. You've seen that. Of course, you've seen rivers and streams. They have current to them. That means that water is moving at a particular rate, That means a certain amount of water per second. The faster it moves, okay, the faster the current, the more water per second. Electricity is kind of the same way, except the water isn't water in electricity. The water is electrons in electricity. Okay, all right, okay, yeah. Again, it could be protons, it could be positive things moving, but typically that doesn't happen unless we have a solution of something. So when we're talking about wires, we're talking about electrons. So it's about the flow. Current is the flow of the electrons. For us, it's going to be about electrons flowing. So electrons, there's a rate there. That means the amount of electrons per second. So the amount of electrons per second, and electrons are a particular kind of charge. That's right, charge. So this is the amount of charge per second, and we measure charge in coulombs. Coulombs, you remember that from the last unit. A coulomb, big, all right, big, coulombs, big. Coulombs per second. So coulombs per second is a rate per second. Means that's a rate, like your speed limit. You're speeding, going down, the speed limit might be 35 and you're going 40. Don't speed. 40 miles per hour. It's a rate. Okay, you put that over time. So this is coulombs per second. And coulombs per second is, a lot of times in physics, when you have a couple of units, you put them together, you get some special unit. Well, we do here. We do. Coulombs per second is called an ampere. But we usually shorten that and say amp or amps. All right, so coulombs per second is an amp. So if it was 1 coulomb per second, 1 coulomb per second, flowing along. And by the way, a coulomb is a butt-ton of electrons. Remember that? Yeah, it's a butt-ton of electrons. So a coulomb would be 6.25 times 10 to the 18th electrons. That's a lot of electrons per second. Okay, that would be 1 coulomb of electrons per second, and that would equal 1 amp. Right? That would be 1 amp. And so that's electric current. Electric current is the flowage of electrons. Now, there's actually a little, there's a myth about electricity. When we turn the lights on and off, hang on, I'm gonna go shut the lights off. Hang on. Lights off, lights on, lights off, lights on. Okay, when we shut the lights off and then we go ahead and turn them on, when you're here by the switch is, it's over there, like 8 feet away from me, and the lights are all over the room. As soon as I turn that switch on, we have this misconception that electricity is going from that light switch all the way to the back of the room instantaneously. And man, those if that was true, those electrons would be just zoom, flying right along so fast, like Speedy Gonzales. You couldn't even see them. They don't do that. If electrons move through wires that fast, those wires are just disintegrate with all that heat that's generated. You have a bad day. That's called an electrical fire. We'll talk about those in a later video. Yeah. So no, that's a misconception. The idea that electrons are flying through the wires to get to, turn the switch on, turn the light on with the switch going, close that switch, then boom, lights come on. No, they're not moving very fast at all. In fact, electrons, they do move. They do move when you, turn the lights on in the wire. They move it around a rate of, you ready for this? The huge velocity of about 1 meter per hour. Yeah, that's right, 1 meter per hour. So electrons are going really slow, and they get about this far in 1 hour with 120 volts. So they're not moving very fast at all. Then how come the lights turn on in the back of the room when you flip the switch? How do they turn on so really fast like that? That's a good question, Billy. And the reason is because the electrons that are in the light bulb, okay, so you got your light bulb. Draw a light bulb here, light bulb, light bulb, light bulb. Okay, here's your light bulb. It doesn't look like a light bulb, it's kind of disgusting. All right, so there's your light bulb. And so you have this filament that goes boop, 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 like this in the light bulb. Okay, with me so far? And the electrons are already there. There's electrons in that filament. Of course, it's a wire, right? I mean, it's a wire. Of course it has protons, neutrons, and electrons making up all the material. So the electrons are already there. The electrons are just sitting there in that light bulb, all right? Or if it's a fluorescent light, it's the same idea with a fluorescent light, except you have a gas inside that gets excited. But there's still electrons there, and they're ready. They're like Keanu Reeves, just sitting there going like this. Come on, bring it. Bring it, bring it, you won't, you won't, you won't. And then you do. And then what happens is the electrons that are already there will start to move. They vibrate back and forth with AC current, alternating current. Oh, yeah, the two different kinds of current. We got to talk about that. Yeah, with current, there are two kinds. There's AC and there is DC. AC, DC, for those about to rock, we salute you. Yes, we do. Yes, we do. AC, DC. Quality band. Now, alternating is what AC means. That means the electrons and the electricity actually goes back and forth. It actually alternates direction. So the electrons in the light bulb and AC, you know, typical AC is what you use for electrical stuff in the house, and everything's connected in AC. Yeah, it is. As opposed to DC, which is like battery stuff. Okay, household circuits, AC, alternating current. The current alternates and the electrons move back and forth. With DC current, direct current, that's what we get from batteries. Batteries, electrical generators, batteries. You can have a generator that's DC, but the electrical generators that produce electricity, you and I are, using all the time is AC. DC is out of a battery. That's direct, one direction, okay? You've heard of One Direction. They broke up several years ago. I was so upset. They were so hot. I'm so bummed that they broke up, They were such good music, they were. Okay. So One Direction is the flow of electricity in a direct current circuit. But alternating is... But it doesn't make any difference if it's this or this. What happens is the electrons are already there in the device that you want to power, ready to move. And when you flip the switch or connect your batteries and turn the thing on, press the button, or whatever you do to connect and full circuit it, when you make a full circuit out of it, okay, what happens is you get an electromagnetic pulse that moves at the speed of light. So it's a signal that's sent out to those electrons in the bulb, way back in the room. From when I close that switch, okay, speed of light, it tells those electrons to start moving. So it's the signal that travels at the speed of light. It's an EMS pulse, and it sends out that signal saying, move, okay, and the electrons start to move. They're already there. Okay, but the electrons do move through a circuit very slowly, but that's not the reason the lights turn on in the back of the room instantly. It's because of the speed of light pulse that was sent back to them, telling them to move, groove, shake, and or bake. Okay, all right, so we got that. And I think that's called drift velocity. The electrons moving at about 1 meter per hour. There's a word for that. It's called drift velocity. The electrons will very slowly drift along, but the pulse is being sent, telling them to vibrate. All right, current. Flow of electrons, so we've got two different kinds of current, AC and DC. We're going to be basically focusing on DC current. And we do talk about AC current. Yes, we do. Electromagnetic induction, we'll talk about that, but for the most part, we spend most of our time in circuitry talking about DC, direct current, battery kind of stuff. Okay, AC current is done the same way, essentially. You can figure the same things out. All the math works. The equations work with both of these. But we'll just mostly talk about this stuff here. It's a little bit easier for introductory to electronics and stuff like that, circuitry, when we talk about DC. Okay, all right, I think we're going to wrap this one up. Yeah, we got current, flow, electrons, and yeah, that's about it. Okay, talk to you later.